Hi all, welcome to the talk on Bayesian Generative Adversarial Nets with Dropout Inference. I'm Raja and this work was done as part of my MTech as an internship at IIT Hyderabad with Dr. Srijit PK. Let's start. I'll first be talking briefly about the problem and introduction to the problem. Then I'd give a brief overview over the background that is required to understand the problem, followed by the actual approach that we took, and ending with the results that we have got. So let's start with the introduction. Generative adversarial nets are one of the most popular approaches to generate data from complex data distributions. However, they suffer from a problem called mode collapse. As you can see below, on the left you have original MNIST data and on the right you have data generated by a GAN. Many of the digits that are present in MNIST are missing in the generations by the GAN. So the GAN is not able to capture the entire data distribution of the training set. This problem is known as mode collapse. Bayesian GANs were introduced to address this issue using Bayesian principles. So instead of learning a single point estimate as the parameter, Bayesian GANs learn a distribution over the parameters of the GAN. But analytical inference is intractable in neural networks. Hence, Bayesian GANs go for an approximate inference method, which is a variant of Markov chain Monte Carlo sampling method called stochastic gradient Hamiltonian Monte Carlo sampling to get samples from the posterior. The problem is that this inference method requires expensive computational resources and high training time. Can we overcome these issues without compromising on the sample diversity generated by a Bayesian GAN? So, our idea is to develop a Monte Carlo dropout based Bayesian GAN to overcome difficulties involved with the inference in Bayesian GAN with SGHMC inference. And then we show the effectiveness of the proposed method in overcoming mode collapse on various synthetic and real world datasets. Let's come to the background, starting with generative adversarial networks. Here you can see the generator and the discriminator parameterized by phi-g and phi-d respectively. The noise is fed into the generator and it generates samples, and the discriminator is fed training samples as well as the output of the generator, and it is supposed to distinguish between the real and the samples that are generated by the generator. The generator and the discriminator change their or modify their parameters based on the following objective function. This has been written in terms of minimizing as a loss so that it can be expressed as a loss function. Now let's come to Bayesian generative adversarial networks. You can see that the phi-g and phi-d, the earlier parameters, are replaced by theta-g and theta-d, which are random variables. As we are considering a distribution over theta, the parameters of the GAN, we consider the parameters to be random variables now. The inference in Bayesian GAN is made with the help of Markov chain Monte Carlo method called STHMC as described before, using the following relation or conditional posterior format. Now let's go to Bayesian neural networks with variational inference. So a Bayesian neural network parameterized by omega is actually coming up with a distribution for omega by the posterior distribution of over omega, p of omega. However, in the variational inference technique, we instead use an approximating or a variational distribution called q. Instead of approximating p, we try to minimize the distance between p and q. So the following objective function has been derived by reducing the KL divergence between the actual posterior p and the the variational posterior q. Formats like reparameterization trick and Monte Carlo sampling techniques have been used to result at this objective function. Omega is expressed as a function of theta and epsilon, where theta is actually the variational distribution parameter and epsilon is sampled from an independent distribution. This objective has been found to be equivalent to the objective that we can derive from a Monte Carlo dropout inference. Here, the Bayesian network, here we have a functional format for the earlier G function, where omega is a product of a matrix with diagonal elements epsilon and theta, which is the deterministic parameter of the neural network. The epsilon is sampled from a Bernoulli distribution, which is having the parameter of the dropout rate. The following is the objective for the Bayesian neural network with dropout inference, and this has been found to be equivalent to that of Bayesian neural network inference with considering a Bernoulli approximating distribution. The only difference is the regularization term and the prior term, the KL divergence between the prior term. Both have been found to be equivalent if you substitute the prior to be a Gaussian. Hence, doing variational inference with Bayesian neural network is same as doing an MC dropout inference, and we can replace the entire difficult mathematics with a simple dropout layer. Now we come to our approach, which is the Bayesian GAN based on Monte Carlo dropout. We can see that the random variables theta g and theta d can be expressed in terms of the variational parameters phi g and phi d with the help of epsilon, which is sampled from a Bernoulli distribution. I will show you the generator objective in detail. Variational inference starts with KL divergence, minimizing the KL divergence between the posterior and the variational distribution. The KL divergence is written as below. Following simplification by removing the interactable evidence term and substituting for the log posterior values, we arrive at the following objective function. And then to remove the intractability of the likelihood term, we do reparameterization trick followed by Monte Carlo integration of the likelihood term and arrive at the final objective function. Now, if we start with Monte Carlo dropout inference, we can see that we start at the generative loss function, which was given in the previous slide, and then we add stochasticity in the form of dropout and L2 regularization to arrive at the following objective function, where the parameters phi g and phi d are replaced by theta g cap and theta d cap, which are the instances of the random variables due to the randomness introduced due to the dropout. Now we transfer the stochasticity of the random variable from the weights theta to the dropout vector epsilon. Once this is done, we can see that both the objective functions have the same format. This can be extended to the discriminator objective as well. So this is our model. Now let's come to the results. We can see that the scatter plots on the left of 3 data sets, and the second column contains the results of GAN, the third column contains the results of Bayesian GAN, fourth column contains the results of BT GAN, which is an approach, and finally we have W GAN. We can see that BT GAN is actually doing a good job of getting results from the modes. Now to see density, we look at density plots to see how good is the GAN generating from all the modes. We can see for BD GAN it is doing a pretty well job of getting samples from all the modes, hence avoiding the mode collapse problem. Now another concern would have been sample quality. What if the sample quality of the proposed method was too low? But that's not the case. We can see that it's capturing all the modes in the data as well as maintaining at least a minimum sample quality, and in the case of 2D grid it is having the highest quality. Now we come to the real world data sets. Fashion MNIST, we can see that BDGAN is able to generate from all of the modes. You can see bags, we can see shoes, we can even see sandals, which shows that it is able to capture the variation even in real world datasets. This extends to the MNIST dataset as well. We also did an analysis on how dropout varied with respect the variation of dropout, how did it affect the mode collapse problem. So as you can see, the dropout rate increasing did result in better results. If you look at 0.5, this is less variation in the results, but when it comes to 0.9 dropout, we can see there's much more variation than before. Now we look at the training time analysis. We can see that our method BDGAN is almost takes only 1/3 that of the time that is required for the Bayesian GAN. This is a huge boost if you're considering large network training. And we also look at the memory usage. As you can see on the left, we have Bayesian GAN, on the right we have BDGAN, and on different rows we have the real and the synthetic data sets. So in both the cases we can see that the BDGAN or a proposed approach takes much less memory usage than that of Bayesian GAN. Compared to the 82% taken on MNIST by Bayesian GAN, the BDGAN only requires 47% of the memory power. The same follows for the synthetic data as well. To conclude, an efficient yet simple inference technique for Bayesian GANs was established by establishing a connection between dropout in GANs and variational inference. Experiments were run on 3 synthetic datasets, MNIST and Fashion MNIST, to showcase the precedence of the proposed method in the problem of mode collapse. The future work is to extend this work to DC GANs with the help of drop log or even Monte Carlo dropout in convolutional neural networks. Another idea would be to devise a systematic way to perform dropout so that we can identify dropout masks pertaining to particular areas of distribution, which can help us conditionally generate data with the help of the dropout mask. Thank you for listening to our presentation. Please have a look at the references if you want to know more information.